right, here's example number 2 now. This time, we've given you the original data set, not the summary statistics as in the previous example. So why don't you go ahead and pause the video and take a minute to read through this. All right, so if we look at part A, which says check the conditions to be able to create a t-interval. Well, it doesn't tell us what the original shape of the distribution was. And secondly, there's 15 data values, so our sample size is 15. So right now you would think, well, we can't do this problem. However, let's go ahead and graph the sample. And if the sample is fairly uniform and bell-shaped, or excuse me, not uniform, but symmetrical and bell-shaped, then, ladies and gentlemen, the chances are that the population is also probably symmetrical and bell-shaped. Okay? So let's go ahead and graph this data set. So we're going to have to use our ArtiStat app. I'm going to highlight these data values so I don't have to type them in. You'll have to type them in. Now again, this is quantitative data. So if we go to our stat app here and I go to up at the top, since we're going to graph this, let's go to exploring quantitative data. And you've all done this before. Your own data. This data represents ages of race car drivers, and it's in years. So I'm going to paste the data in there. And then the histogram, the bin widths are too big, so I'm going to put it all the way down to 3. And if you take a look, whether you look at the histogram or whether you look at the box plot, or heck, you could even look at the dot plot if you want it. Well, let's not look at that. Let's look at the stem and leaf plot. You'll see that we do have a fairly symmetric and unimodal shaped data. So we can, if the data is fairly normal, then chances are the population is also fairly normal. And the other good thing about this is we get the mean of the sample, we get the standard deviation, and there's our sample size, which are our summary statistics, which we can use. So I'm going to go back now. So first of all, can we use the t-interval? Yes. And why is that? Because even though, extend the page, so we're saying even though our sample size is 15, which is less than 30, and we don't know the shape of the population, so our sample size is less than 30. We don't know the shape of the original population. However, the sample is fairly normal. So in this case, I keep saying we can construct a t-interval. Now, if that shape of the sample would have been inconclusive, if it would have been fairly unimodal and bell-shaped, then you know what? We couldn't do this problem. We just skip and go on to another one, or skip it altogether. So now, for B, let's go ahead and construct a 98% confidence interval. Well, again, I'm going to use the information from the problem. We know that our sample size is 15. The sample mean was 31.9. The sample standard deviation was 4.76. Now that means that the degrees of freedom, which would be 15 minus 1, that's 14. And all we need left now is to figure out what is that critical value, t of alpha divided by 2. Well, let's go use our stat app one more time, okay? And this time what we're going to do is we're going to go to the t-distribution. Maybe. Let's try this again. There we go. And remember, we're going to find percentile quartile, because this is going to give us our critical values. Now, again, our degrees of freedom was 14. We always, on a confidence interval, want to use a two-tailed because we're splitting that alpha up. We want the middle, and we want the middle 98% this time. Remember, this value right here should match your confidence interval. So this is 98%, and you'll notice right here, 2.624 is our critical value. So I'm going to go back to here, and our critical value is 2.624. Now again, I'm going to probably go over a little bit over the 7 minutes here, but I'll try and do this, like I said, as best we can. So remember then, your confidence interval is your sample mean plus or minus your critical value you just found times your sample standard deviation divided by the square root of your sample size. So if we do that, that would be 31.9 plus or minus 2.624 times 4.76 divided by the square root of 15. You don't use 14 here. Remember, this is your sample size. This is n, it's not your degrees of freedom. The only time you use your degrees of freedom is to find your critical value. So basically what that means, that's 31.9 plus or minus 3.225. And if you take this 3.225 and subtract it from 31.9, you get 28.7. Now I'm going to round to the first decimal place because our original data was a whole number. Remember, our rounding rule says go one place past the original data set. That should be, our population mean should be between that lower confidence limit and the upper one, which we get by taking 31.9 plus 3.225, and that's 35.1. So we believe that the population mean should be, in other words, the average age of all race car drivers should be between 28.7 years old and 35.1 years old. Now, I'm not going to use a label here, ladies and gentlemen, because generally when we ask a person for their age, we don't usually give a label, but you should always label your two limits in your confidence interval with whatever label the original data was.